All right, so I'm Clement. I work at a French company called Provadis, and indeed I'm going to talk about abusing privileged file operations for privilege escalation on Windows. So privileged file operation bugs are when you have privileged operations that are performed by, file operations that are performed by privileged processes. And if a non-privileged user has some sort of control over this file, then you may have a problem. Some examples that are well known to pen testers are here. For instance, if you have write access to an executable file that is used by a service, a privileged service, then obviously you can get your payload to be loaded as the account used by that service by just overwriting the exe file if the service is not yet running. We're going to see some other example of this type of bugs. And because these are logic bugs, they're usually very stable. There is no memory corruption involved. And they often survive code refactoring. So as long as the file manipulation logic does not change, you can find the same bug in several versions of the same product. And the thing is, to find this bug, or at least the low-hanging one, most of the time we don't have to start a tedious process of reverse engineering. We just have to fire up our favorite process monitor or a debugger and start looking at what the privileged process are doing with our files. And obviously, we'll need a way to also check ACLs on the file. So just explorer.exe is fine, but you can also use access check, for instance. And the techniques and tools that we are going to use to exploit this type of bugs were published by James Forshaw. In numerous blog articles and conferences. So I would encourage to watch his influential talk, for instance. And he also implemented them in a toolkit and a library that we can use when the built-in tools do not exactly fit what we need. And these techniques and tools made, in my opinion, this type of file system attacks a new kind of low-hanging fruit for privilege escalation. So the first technique is a simple NTFS moon point or a junction, which basically works as a redirection from one directory to another. So you can think of it as a kind of symbolic link that only works on directories. So here, for instance, if I have a privileged application that tries to access cdir file.exe, it will actually access cother file.exe. And while unprivileged users on Windows system cannot create a file system symbolic link, there is a specific privilege for that is only granted to administrators by default. They can create symbolic links in the object manager namespace. And if we combine, and this symbolic link can point to files. So if we combine this with a junction that points to an object directory, in which we created a symbolic link, we can have something that works similarly as a symbolic link. So here, if the application tries to access cdir file.txt, it will actually open cotherstuff.ne. And to exploit arbitrary file write bugs, we can, of course, replace the existing binary or config file if we can override them, or do a basic DLL hijack and drop a DLL if, of course, we can restart the process. One example is the wow64 log.dll. Because this DLL does not exist by default on Windows system, but if it does exist in the system32 directory, it will get loaded in every 32-bit processes started. So if you have a privileged 32-bit process, this is a nice one you can try to drop on the disk to get code execution. And another one is another trick by James, which is using the diagnostic hub service that runs as a system. And using specific com calls, this service can be made to load a file with any extension. So for instance, a .txt file, as if it were a DLL, as long as that file is in system32. So we will use the bugs to drop files in system32 and then use this trick to have a privileged service load our file as if it's a DLL. A typical example for this type of bug is arbitrary file write in the logging feature of a product. And this needs three ingredients. The first is a log file with a permissive ACL. So for instance, here everyone has full control over the created log files. The second is that the file is created in a user writable location. So for instance, in program data, this directory is really interesting because by default, a privileged user can create new files and directories, but not modify existing one. So if we can use this folder, for instance, if we can create files in this folder, this will allow us to perform some attack, as we will see later. And the third ingredient is a write from a privilege service or process. So to exploit this type of bug with the DiagHub services, for instance, we can delete existing log files because everyone has full access to them. Replace, because we have write access with the default rights of program data subdirectories, we can replace the logs directory with a junction that points to system32. So when our service will try, our product will try to create the log, it will actually create it in system32 and set the permissive ACL on it. And because of that permissive ACL, we can replace the content of the log file with our DLL and start the DiagHub service and have it load our file and gain system code execution. To do a more generic DLL hijacking, we can do basically the same thing, except that we replace the logs folder, we turn it into a junction to an object directory in which we create a symbolic link with the same name as the file the process is going to create that points to the file we want to create. And here we can also have an arbitrary file name. Then the product will follow these redirections and create our file, and again set a permissive ACL so that we can override the content of the file. And then when our process starts, if we drop the DLL in the right directory, it will load it and execute our code. So this is this pattern is basically an unsecure implementation of a common need. So multiple components with different access levels that all need to write log files. And when it's implemented like this, you get basically an exploitable condition. And multiple instances of this specific bug were found in multiple products. This is just over the last year or so. But in this example, of course, we have a really easy exploitation method because we have a permissive ACL that is set on the created file. So it's quite easy to see how we can get write access to the file. But for the general case, for instance, if we drop a file in system32, it will inherit the permission from the parent folder. So we won't be able to modify the file and put our payloads in it. So what we can do is target different operations. So staying with our log file example, we can target the log file rotation. Maybe the product has a rotation feature that we can abuse. It will, for instance, rename the log file. Let's say it's abc.log. It will rename it to abc.all.log, for instance. And we can target this operation by replacing the source and destination to, so we replace the source by a link to our payload and replace the destination by a link to the file we want to create. So when the product will perform the operation, so for instance, we made our payload big enough so that the product thinks, oh, okay, the log is too big, I need to rotate. It will do the move or rename operation and actually move our payload to the target location. So this way, we have defined the content and the location of the file. So we see that we can look at some file operation as kind of exploit primitive, and some of them are very powerful. For instance, of course, a move rename, but also if you can control a copy. So if you control both source and destination, it's basically the same thing. And if you control the source, but not the destination, but the destination is somewhere the unprivileged user can read, well, then you got an arbitrary file read, and you can try to exploit this to read secrets. And again, we can use Procmon or a debugger to see if everything works. And some operations do require precise timing, as you can imagine. And for this, there are op locks, which are which are locks that you can put on files that will allow you to get a callback whenever another process wants to access this file, and the other process will be blocked from accessing the file as long as until you leave the lock, until you release the lock. So this is obviously useful to block processes at arbitrary times so that we can reliably exploit and win some race condition. And of course, we can combine this with previous techniques. So here we are, our pseudo symlink again. And if we can place an op lock on the file, when the file gets accessed, we can change the symlink, so not the file, but the symlink, to point to another file. So if we remember that our application tried to access cdr_file.txt, it will actually access the first file on the first access, and all subsequent access will go to the second file. AV is obviously a nice target for this kind of file because they will manipulate a lot of, sorry for this kind of attacks, but because they will manipulate a lot of files and they will manipulate them with high privileges. And often many operations from AV can be triggered by unprivileged users. Just dropping, for instance, a file on the file system will trigger, for instance, a scan. And it has a lot of abuse potential. These are typical operations that your AV will do. And there are as many potential roads to privilege escalation. And some AV will perform very interesting operations when they detect an infected file. So, for instance, they will create temporary copies of the file in the same folder, or try to rename the file, but still in the same folder, or stuff like that. And a little demo. So here we create a directory test, and we drop ecar in the directory. We sleep a little bit. We see that our ecar file got detected. And here we set an op lock on a specific log file because we know that this log will get written to just before a copy of the infected file is performed. So we use the set op lock tool to place an op lock on the file, and we wait. So I shortened it a bit, but in the original video it was something like 1 minute. Okay, the op lock got triggered. So now we remove the directory we created, and we replace our file, so our infected file, ecar.txt, by a symlink to our payload. So here, get system shell.exe. And we replace the destination, so the copy that the privileged process will create, by a symlink to the file we want to create. So we create a symlink and have it point to ulu_handler.exe. And we use the bait and switch, which implement the switching method seen before, to have it point just after the copy to somewhere else, because obviously the AV at some point will destroy the copy he's made, and we don't want it to destroy the file we just created. And once this has been performed, the ULU handler is actually the executable that is used to perform the update on this service, and the update run as system. Thank you. Other ways to abuse file deletion in a more generic sense, but still when they're performed by AV or other stuff, but mostly AV, is to exploit the delete to delete file that we can later replace. For instance, in program data or C Windows temp, where unprivileged user can create file, but not replace existing one. So if we can delete this file, they no longer exist, so we can recreate them. And then, if a privileged process, either the same process or another process, use this file, well, we are back to the same situation as trying to exploit an arbitrary file write, because we own this file. So it's like a privileged process accessing user-owned file. And AV target is not the only it's an obvious target, but you can also use this, for instance, to exploit any kind of software that do not check for pre-existing files, like installers. And another trick we can use with AV is try to redirect a file deletion. So if we have a talk-to in the file deletion process, we drop the ACAR payload or anything malicious. So maybe not the first version of Mimikatz, but another one, somewhere in the directory. And wait for it to be detected. And before the deletion, but after it's detected, we replace the directory by a junction to system32. And you can easily guess which file will get deleted by the AV. So these are some bugs that were reported over the last year or so as part of this research. Not all of them are patched. The PureSecure one, the CV indicates that it's patched, but in my testing with the last version, it's not. So you can, I'll show a link later. And to prevent this kind of bug, obviously the applications, the privileged application, need to not break the security boundary in the first place. So either impersonate or your restriction token, or do some architectural change so as not to access user-controlled files. And they need also to take into account this kind of attacks when they harden the product. And defenders can try to detect this because it will potentially generate some log depending on the activity. For instance, if you start dropping ACAR everywhere, and it will also have some weird behavior like creating oplogs and using junctions and stuff like that that is not performed by your typical application. There are some more examples at this link, and I don't know if we have time for some question, but otherwise you can catch me later. And there is also a blog post version of this talk at the same address, so that you can just go there and read everything.
Thank you for the great technical talk. I think we have time for one question.
When taking advantage of this, let's say I have some fully obfuscated Cobalt Strike payload and several team servers set up so that I can do kind of that shuffle dance and have persistence. In doing this, will this prevent the original executable from operating correctly as it should have? Like, for example, will that AV scan normally, or will there be something that might seem suspicious to the user?
So this, I think, would depend on which file you target, for instance, and how you implement your payload. So, for instance, if you're dropping a DLL somewhere that will get loaded by a privileged process, and that privileged process performs some important task, well, of course, if you don't correctly implement the callbacks to the original DLL, then you will probably prevent the process from working as expected. So you might want to avoid that. But otherwise, you can, for instance, if you're targeting a completely separate service, like using the jack-up trick, then that shouldn't be a problem, because it's not something that is supposed to be critical for most use cases.
Okay, thank you.
Thanks.